Hello, and welcome to TI Precision Labs. Today we'll be discussing assembly. First, what is assembly and why do we use it? Assembly is a middle ground between C code and machine language. Assembly was one of the first ways we started abstracting from machine code, as it was much easier to read than having to decode ones and zeros. Being familiar with assembly is also important for understanding what is changing on the physical registers of devices, which can be beneficial for optimization and debugging. So how does C code, assembly, and machine code relate? First, we'll start with our C code, which is where most programmers start now. C code is considered human readable and is the easiest to understand. To get from C code to assembly code, the C code needs to be converted. This can be done automatically by a program called the compiler, which compiles or converts our C code into assembly. The compiler will also optimize your C code and help save memory and program cycles. Now, how do we get from assembly to the machine code that our processor will understand? Through the assembler, the assembly code gets turned into machine code for the CPU to process. The assembler's job is to take the instruction and its format and convert to ones and zeros the core is expecting. Machine code's format typically consists of an opcode in the first byte, which dictates which instruction will be performed, and the rest of the bytes include the operand, which are parameters for the instruction. So how do we read assembly instructions? To demonstrate, let's take an example from the MSP430 instruction set. Reading from left to right, we start with the instruction itself. Here our instruction is add. The instruction will dictate how the operands are formatted and can change depending on your instruction set. With basic double operand instructions, there is a source operand and a destination operand. The source operand tells the CPU where to get the data from, and the destination operand tells the CPU where to store the data. With the add instruction, the CPU will receive data from the source and then add the data to the data stored in the destination. Throughout this presentation, green will represent the instruction, red the source, and blue the destination. Here are some further example instructions. The single operand instruction includes the instruction and a single destination operand. The triple operand instruction will contain two source operands and a single destination operand. The no operand instruction will contain just the instruction and will sometimes contain a label. This label tells the program counter where to go for further instructions. Now let's go through an example of assembly. Let's start with C code. In this simple example, we initialize four variables, w, x, y, and z. Then we will assign values to these variables. The program will then add w, x, and y and store the result into z. Beside the C code is the compiled assembly code. As we can see, the C code doesn't get compiled one-to-one. This is because the compiler will optimize our C code. In our example, all the value assignments were optimized out. Sometimes a single line of C code will require multiple lines of assembly. This is shown with the line z equals w plus x plus y, consisting of several moves and adds. Let's step through an assembly example and see the register changes. We will look at the core registers in this example. The first core register we will monitor is the program counter, labeled PC. The program counter tells you where in memory the code is being executed from. This is important when you are analyzing the memory. The second register we will watch is R12. R12 is a default register and has no special properties. The last register used in this program is R15. Like R12, it is a default register with no special properties. Let's move on to the first instruction in main. The first instruction is moving hex 3 into register 15. When stepping to this instruction, notice the program counter is at hex C00E. This lets us know that the first instruction in main starts at this address in memory. Executing the line, we can see the move instruction successfully updated R15 to hex 3. The move instruction will simply move the value of the source, or the first operand, into the destination. After executing the line, we can also see the program counter change. The program counter will move after each executed line as it steps to the next instruction. The program counter was incremented by 4. Since these instructions are next to each other in memory, the previous instruction was 4 bytes long. The program counter points to our next line in code. Here we have an add instruction. Here the program will add 7 to the value of R15 and keep the result in R15. Let's execute the line. Once executed, the result of 7 plus 3 is stored in R15. Remember, hex A is decimal 10. The program counter is also updated here. Again, the program counter was updated by 4. Moving on to the next instruction, the program will move hex 11, which is decimal 17, into R12. When we execute the line, we can see the value hex 11 is now stored inside R12. The program counter increments as well to the next instruction. Going on to the next instruction, we have another add. This instruction adds R15 to the value inside R12. When we execute this line, the value of ART12 is now updated to hex 1b. This is equivalent to 27 in decimal. The program counter is also once again updated. The final instruction is the return instruction. This will return us back to the stack and continue on with the rest of the program. So this is the end of the program for this example. In a real application, this would return the program to the last function call if there was one. Let's now execute the return and watch the program counter and stack pointer registers. On the last instruction execution, we return to the top of the program to reset. This is shown with the program counter getting set to hex C000, which is the start of the program. The stack pointer also gets updated here as well. As our program returns, data gets popped off the stack, therefore the stack pointer increments. Here we show different instruction sets to demonstrate that assembly language will vary depending on your CPU core. Each one will have its own instruction set, which details the commands in the format that the processor will accept. The ARM M Cortex and MSP430 core instruction sets are shown here. Depending on your CPU, you will have different instructions and formats, but can expect similar types of operations to be performed. The image on the left shows that even within the ARM Cortex, there are a varying number of instructions depending on the specific core. As we can see here, the simple add instruction is formatted differently between ARM and MSP430. The ARM Cortex standard is the instruction, then destination, then operand, whereas the MSP430 core will expect the instruction, then the source, then the destination. If a programmer isn't careful moving between instruction sets, they can end up with their data in locations they are not expecting. So when programming an assembly, it is important to reference the documentation for your CPU. This concludes our video on assembly code. Thank you for watching. To find more technical resources and learn more about TI microcontrollers, visit ti.com/microcontrollers.